The universe has truths that just don't line up with common sense. Physics gives us this elegant set of equations, a whole tapestry. But if you look closer, there are threads that don't fit. There are knots you can't untie, and these aren't just puzzles. They're deep cracks in our understanding. They force the smartest people we have to question everything they thought was true. So here are 20 physics paradoxes that are mind-bending. They show the potential flaws in our best models, the limitations. It gives you a new perspective on reality. You start to see where our knowledge actually ends, and where the real mystery begins. Time might not be a river, it might be a maze. Empty space might hold the key to everything. Each paradox is a doorway to a deeper layer of the cosmos. This will challenge how you see everything, from the atoms in your hand all the way out to the edge of the observable universe. So what's the most fragile part? What part of our understanding of reality is the most fragile? The first thing that breaks our everyday sense of reality is a pair of twins. Two brothers born at the same moment. One stays on Earth, lives a quiet life. The other gets on a starship, traveling near the speed of light, heading for a star 10 light years away. And according to Einstein, each brother would see the other's clock running slow. To the astronaut, Earth time seems to crawl. To the one on Earth, the ship's clock lags behind. Then the traveling twin comes back after 20 years, and there's a contradiction. They can't both be younger than the other. So who's right? That's the twin paradox. And the solution shows a flaw in our intuition. The situation isn't symmetrical. The twin on the ship isn't just moving at a constant speed. To turn around and come home, he has to accelerate. He changes his speed and direction. That acceleration breaks the symmetry. It tells the universe which twin actually took the journey. And the physics, when you include that, gives a clear answer. The traveling twin comes back to find his brother has aged much more. This isn't just a thought experiment. We've measured it. Atomic clocks on airplanes, moving much slower than light, come back to the ground showing a tiny difference. A measurable difference compared to clocks that stayed. Time stretched for the traveling clock, and that forces a question. Is time a single river, flowing at the same rate for everyone, everywhere? The answer from this is no. Time is personal. It's woven into your motion through space, your past, your present, your future. They are not the same as anyone else's if you're moving relative to them. The twin paradox peels back that first layer. It shows our most basic feeling about time, that it passes the same for all of us, is an illusion. And if something as basic as time is that malleable, what other foundations are waiting to be questioned? Time is something we each experience, but then you think about the rest of the cosmos. There was a physicist, Enrico Fermi. He helped build the first atomic reactor. One day, during a lunch, he was looking up at the stars. People were talking about how old the galaxy is, how many stars there are, and he asked a very simple question. Where is everybody? The universe is so big, so old. Our galaxy has hundreds of billions of stars. A lot of them have planets. The numbers seem to say life should have started many times in many places. Some of those civilizations would be much older than us, more advanced. They should have spread out. We should see their signals, their artifacts, their presence. It should be obvious, but we don't hear anything, we don't see anything. That's the Fermi Paradox. It's this contradiction, the high probability of other life, and then the complete silence we actually find. An astronomer, Frank Drake, tried to put numbers to it. He made the Drake equation. It's a way to guess how many talking civilizations might be in our galaxy. You put in things like how many stars form, how many have planets, how many planets could support life, where life actually begins. The trouble is, we don't know most of those numbers. The equation doesn't give an answer. It just shows what we don't know. It shows all the places we could be wrong. So where is everybody? The answers are unsettling. One idea is the great filter. It's a barrier, a step in evolution that's so hard, almost nothing gets past it. The scary thought is that the filter isn't behind us. It might be ahead of us. It could be something that always destroys a technological civilization, like self-destruction, war, or wrecking the environment. The silence might be a warning. Other ideas are less grim but still strange. Maybe when a civilization gets advanced enough, we just can't recognize it. Their technology might look like natural events. Or maybe they lose interest in expanding. They go into virtual worlds instead. There's the zoo hypothesis. The idea that they know we're here but they don't interfere. They watch us like we're in a preserve, or maybe we are alone. The conditions for complex, intelligent life might be so rare. We could be the first, or the only one in this part of the galaxy. Think about what we've done. For about 100 years, we've been sending out radio and TV signals. That bubble of noise is a tiny sphere, only about 200 light-years across. The Milky Way is over 100,000 light-years wide. Our signal is less than a drop in that ocean. An alien civilization would have to be very close, listening at exactly the right time with the right tools to even hear it. We're whispering in a hurricane. The Fermi Paradox shows a flaw in how we think. We assume life is an inevitable chemical process, that intelligence is a natural outcome of evolution. But the empty sky suggests something else. It makes us face our own naivety. Are our models for astrobiology all wrong? Is life, or conscious life, just a cosmic accident? Something incredibly rare. The paradox isn't just asking about them, it's holding up a mirror, asking what our own future might be in this immense and silent universe. There's this other silence, inside a sealed box. It's a thought experiment from Erwin Schrödinger, meant to show how strange the quantum rules are. He put a cat in a box with a vial of poison, a radioactive atom, and a hammer. If the atom decays, the hammer breaks the vial. The cat dies. If it doesn't decay, the cat lives. But in quantum theory, the atom is in a superposition. It's both decayed and not decayed at the same time. So Schrödinger said the cat must be both alive and dead. A blurred mixture. Until someone opens the box and looks, that's the measurement problem. It asks a simple, unsettling question. How does our definite world, where a cat is either here or not, how does that come out of this fuzzy cloud of possibilities? The math for particles, the wave function, shows all possible outcomes existing together. But we only ever see one. So what flips the switch? What makes the wave function collapse into a single fact? That's the deepest crack in modern physics. For a long time, the main answer was the Copenhagen interpretation, from Niels Bohr. It says the act of observation, of measurement, forces reality to choose a state. But that just raises more questions. What counts as an observation? Is it a human mind, a camera, one atom hitting another? There's no clear line between the quantum world and our classical one. That vagueness is the flaw. It means our theory is incomplete, missing a piece. The double-slit experiment shows this strangeness. You fire particles like electrons at a barrier with two slits. If you don't watch which slit they take, they act like waves. They make an interference pattern behind the screen, as if each electron went through both slits at once. But the moment you put a detector at the slits, the interference disappears. The electrons act like little bullets, one slit or the other. Just looking changes the behavior. As if the particle knows it's being watched. So does consciousness create reality? Some have asked. A more radical answer came from Hugh Everett. His many worlds theory says the wave function never collapses. Instead, every possible outcome happens. When you open the box, the universe splits. In one branch, you see a living cat. In another, a different outcome. An uncountable number of parallel realities branch from every quantum event. That solves the measurement problem, no collapse needed. But it asks us to believe in a multiverse of staggering size, where every choice, every chance spawns a new world. So which is more plausible? A universe that needs a conscious observer to make it solid, or an infinite multitude of universes, most of which we can never see? The measurement problem shows a fundamental incompleteness. It tells us quantum mechanics, for all its power, is probably a stepping stone. A brilliant but flawed map. The cat isn't alive or dead. It's a signal, pointing to a deeper layer of reality we haven't found yet. A book falling into a black hole is gone. That was the belief for a long time. But Stephen Hawking looked at it again. He saw that black holes aren't completely black. They should glow. They should give off a faint radiation right from the edge. This Hawking radiation, he said, would just be thermal energy, random heat. It wouldn't carry any information about what went in. So take that book. The story, the characters, the order of the letters, all that information gets scrambled into noise as the black hole evaporates. And that creates a crisis, because in quantum mechanics, information can't be destroyed. It can be scrambled or hidden or changed, but it has to be recoverable in principle. That's a foundational rule. The universe is supposed to be deterministic at that level. If you know the complete state now, you should be able to work out the past and the future. And Hawking's calculation said black holes break that. They're the ultimate shredder. That's the black hole information paradox. It puts Einstein's theory of gravity, which describes black holes, against quantum mechanics, which handles the small scale. And they give completely different answers. Hawking even bet against information loss, and then later said he was probably wrong. The resolution came from a radical idea. Physicists like Leonard Susskind championed it. The holographic principle. It says all the information about what's inside a three-dimensional black hole isn't lost. It's encoded, like a hologram, on the two-dimensional surface of the event horizon. The surface area holds the data, not the volume. And when Hawking radiation escapes, it somehow carries that encoded information back out. It's imprinted in incredibly subtle correlations between the radiation particles. It's like burning an encyclopedia. The pages turn to ash and smoke. To you, the information is gone. But in principle, if you could collect every ash particle, trace every molecule of smoke, track the precise light and heat, you could reconstruct every word. It would be impossible for us, but the information isn't fundamentally erased. It's just transformed, so the paradox seemed solved. But that solution created another problem. A stranger one, the firewall. If information is leaking out from the horizon, then the event horizon can't be the smooth, empty space Einstein predicted. For the math to work, an astronaut crossing the horizon might hit a wall of blazing high-energy particles. A firewall, and that's just as paradoxical, because general relativity says you should cross the horizon without noticing anything. So which is it? A peaceful passage or a violent end? We don't know. The information paradox shows the raw edge of what we understand. It shows that general relativity and quantum mechanics, our two best descriptions of reality, can't both be completely right where gravity is strongest. One of them or both has to break down. The fate of a single book, lost in the darkness, might hold the key to a theory of everything. The strangest observer might not be you or me. It could be a brain. A single brain just floating there. It assembled by chance from random quantum fluctuations in a universe that's otherwise empty and eternal. And this brain, by sheer accident, has a full set of memories, a childhood reading physics, watching this. It believes it lives in a cosmos full of stars and planets. But it's completely alone. That's the Boltzmann brain paradox, and it's not science fiction. It comes directly from our best theories, statistical mechanics. Cosmology. The physicist Ludwig Boltzmann had this idea. In a universe moving toward disorder, rare pockets of order can appear randomly. Given enough time, infinite time, even the most complex ordered structure could form from chaos. A brain with coherent memories. In an eternal, expanding universe, the math says these freak fluctuations should be far more common than observers like us. We evolved slowly on a planet over billions of years. We come from a long, low-entropy past, a universe that started in an incredibly ordered state. But if the universe is truly eternal and chaotic, then our brief, ordered history is an unimaginably rare event. A single Boltzmann brain popping into existence with a fake memory of that history is far more probable. This forces cosmologists into the measure problem. How do you count observers in an infinite cosmos? If the models predict a near-infinite number of disembodied brains and only a finite number of real beings, then statistically, we should be the brains. How can we trust any of our memories, our records, the entire scientific story of the Big Bang, if it's far more likely we're momentary illusions? The paradox exposes a catastrophic flaw. It suggests our understanding of the universe's beginning, the arrow of time, probability itself, might be profoundly wrong. Some physicists argue it means the universe can't be eternal in the way we thought. That there has to be a boundary, a true beginning, something that makes our ordered history not a fluke, but a necessity. The Boltzmann brain is a ghost in the equations. A warning: when you follow the theories too far, they can undermine the very reality those theories were built to explain. It asks a personal question. Are we the result of a grand cosmic narrative, or just a fleeting statistical accident, thinking alone in the dark? Einstein was never comfortable with the randomness in quantum theory. He called it spooky. In 1935, he worked with two colleagues, Boris Podolsky and Nathan Rosen. They designed a kind of trap, a thought experiment to show quantum mechanics was incomplete. That became the EPR paradox. They imagined a single particle decaying into two. By conservation laws, these two particles would have linked properties. Entangled properties like a pair of gloves. If you find a left-handed glove in New York, you know instantly the one in Tokyo is right-handed. But quantum mechanics said something stranger. Until you look, neither particle has a definite handedness. Each is in a superposition of both possibilities. Then, the moment you measure one in New York, force it to become left, the other in Tokyo instantly becomes right. No signal travels between them. The information just jumps faster than light. Einstein called that spooky action at a distance. He argued it proved the theory was flawed. There had to be hidden variables, predetermined instructions the particles carried from the moment they split. The gloves were always a left and a right. We just didn't know which was which until we looked. For decades, that was a philosophical debate. Then in the 1960s, a physicist named John Bell found a way to test it. He devised a mathematical inequality. If hidden variables were real, if everything was predetermined locally, then certain statistical results from measuring many entangled pairs would never exceed a specific limit. But if quantum mechanics was correct, if spooky action was real, the results would violate that limit. They'd show stronger correlations than any local, hidden variable theory could allow. The experiments were done starting in the 1970s, and they came down decisively for spookiness. Bell's inequalities were violated. The universe at its core is non-local. The particles are connected in a way that transcends space. That doesn't mean they're sending a faster-than-light message. That's the crucial nuance from the no-communication theorem. You can't use entanglement to send a signal because the outcome of your measurement is always random. You get a left or a right glove at random. The spookiness is in the correlation. Your random result in New York is perfectly matched instantly by a corresponding random result in Tokyo. It's as if the two particles are parts of a single entity, no matter the distance. This isn't just theory, we use it. Quantum cryptography relies on this principle. If anyone tries to eavesdrop on an entangled photon pair, the act of measurement disturbs the correlation, alerting the users. Quantum computers use entanglement to link qubits, performing calculations in parallel across a connected web. So what does this mean for reality? It forces a brutal choice. Either we abandon locality, the idea that objects are only influenced by their immediate surroundings, or we accept that the universe has a hidden layer of variables that are themselves non-local, influencing things everywhere at once. Both options shatter our classical intuition. Einstein wanted a universe where things happened here because of causes nearby. A clean, local, causal cosmos. The EPR paradox, meant to defend that view, ended up proving it wrong. The fabric of spacetime itself might be an emergent illusion, stitched together from deeper, non-local threads. When two particles whisper to each other across the galaxy, what are they telling us about the true nature of connection? You look up at night and it's dark. That seems obvious, but in the 19th century, an astronomer named Heinrich Olbers asked a question. If the universe is infinite and static and filled with endless stars, then why is the sky dark? In that kind of cosmos, every line of sight from your eye should eventually hit a star. The whole night sky should be a solid sheet of light, as bright as the surface of the sun. But it isn't. That's Olbers Paradox. It's a contradiction anyone can see. Think of an infinite forest where every tree glows. No matter where you look, you'd see a glowing trunk. The whole forest would be ablaze. The night sky should be like that. Johannes Kepler saw this problem centuries earlier. Edmund Halley thought about it too. The paradox showed a flaw in the Newtonian model, a static, eternal, infinite cosmos. Something was wrong with that picture. The resolution came from a revolution. The universe isn't static. It's expanding, and it had a beginning. The key is the finite age of the universe, about 13.8 billion years. Light travels at a finite speed, so we can only see the light that's had time to reach us. We're not seeing an infinite tapestry of stars. We're seeing a finite sphere of visibility, a cosmic horizon. The most distant galaxies are so far that their light has been traveling for almost the entire age of the cosmos to get here. But there's another effect. The expansion of space itself stretches that light. This cosmological redshift shifts visible light into longer, invisible wavelengths, like infrared and radio. The energy of that ancient starlight gets diluted, spread thin by the expanding fabric of the cosmos. So the most distant stars and galaxies don't contribute a blazing glare. They contribute a faint, cold whisper of energy, and that whisper has a name. It's the cosmic microwave background radiation, that faint static on an old television. A small fraction of that signal is the afterglow of the Big Bang. It's the cooled and stretched remnant of the universe's first fireball, now just a few degrees above absolute zero. This is the ultimate source of the light in Olbers Paradox, but it's so redshifted and feeble that it shows up as a uniform, dark glow in microwave frequencies. Not a brilliant sky, so the darkness tells a story. It tells us the universe isn't infinite in time. It had a fiery birth. It's dynamic, growing, evolving. The black between the stars isn't empty. It's a historical record, a limit to what we can see and evidence of a profound beginning. Looking up at a dark sky and wondering why it isn't blindingly bright, that led directly to the evidence for the Big Bang. It shows how a simple question can unravel a flawed model and point toward a deeper truth. A journey to the past creates a logical trap. You step into a machine, you go back decades, and you find your own grandfather before he's met your grandmother. If you stop that meeting, you ensure you're never born. But if you're never born, you could never have traveled back to interfere. So how could the event ever happen? That's the grandfather paradox. It's a classic science fiction dilemma, but it points to a real crack in our physical theories. It's not just a plot hole. It comes out of the math of Einstein's general relativity, which allows for structures called closed time-like curves, paths through spacetime that loop back on themselves. Essentially a tunnel to the past. The logician Kurt Gödel found solutions like this to Einstein's equations. He described a rotating universe where you could literally travel into your own past. This wasn't science fiction to him. It was a mathematical possibility. Later, physicists like Kip Thorne took the idea further. They looked at whether traversable wormholes, these theoretical shortcuts through spacetime, could be engineered into time machines. The concept is staggering. If you take one mouth of a wormhole and accelerate it to near light speed and bring it back, time dilation means less time passes for that end. It becomes a gateway to an earlier moment. You step through and you emerge in your own past, but then the paradox strikes. Could you change that past? The Russian physicist Igor Novikov proposed a principle to save logic. The The Novikov self-consistency principle. It argues the universe is a single, consistent story. If time travel is possible, then anything a traveler does in the past must already be part of established history. Your attempt to stop your grandfather would inevitably fail. A gun would jam, you'd trip at the crucial moment. Some twist of fate would preserve the timeline exactly as it always was. You were always there, part of the past, and your actions never altered the outcome that led to you. This makes time travel a kind of prison of predestination. You have no free will to change things. You're just playing a role that was written before you were born. But what if consistency isn't enforced in our own timeline? Another resolution, popular in fiction, is branching timelines, parallel universes. In this view, the moment you interfere, you don't erase your own past. You branch off into a new, separate reality where your grandfather never had children. Your original timeline and your original self remain untouched. You become a refugee from a history that no longer exists for anyone but you. Films like Back to the Future show the intuitive horror of this. Marty McFly watches his own photograph fade as his actions jeopardize his parents' meeting. The emotional core is this fear of self-erasure, of becoming a ghost in your own life. But which model is more plausible? A single, rigid universe that corrects any paradox, or an infinite multiverse sprouting new branches with every decision? Both answers force us to confront a flaw in our most basic assumption. We experience cause and effect in a straight line. One event leads to the next. But the physics suggests time might be more like a tapestry, where every thread is connected in a loop, or like a tree with countless branches we can never climb back to. The grandfather paradox isn't about building a time machine. It's a tool. It exposes that our linear understanding of causality might be a local illusion. A useful story that breaks down under the extreme conditions allowed by our deepest theories of gravity. Is the past truly set in stone, or is it just a branch we can no longer reach? Nick Bostrom has this argument. It's not science fiction, it's a philosophical position. He starts with a premise. If a civilization gets advanced enough, it could run simulations. Conscious ones, like us, they might run billions of them for any reason, research, entertainment, things we can't imagine. If that's true, then simulated minds would outnumber biological ones by a huge amount. So statistically, we're more likely to be simulated than original. That's the simulation hypothesis. It creates a trilemma. Bostrom says one of three things has to be true. 1. Civilizations like ours almost always go extinct before they get that powerful. 2. They get that powerful but choose not to run simulations. Or 3. We are almost certainly living in a simulation. You have to pick one. Each one has big implications. Elon Musk talks about this. He says the odds are overwhelming we're in a sim. He points to video games. Look at the progress, from simple pixels to immersive worlds in just decades. Now extrapolate that. Over thousands of years, millions, the gap between our reality and a creator's reality could be huge. Like the gap between a Pong character and a modern game. But can we test it? Look for evidence. Some physicists think we might find glitches, shortcuts in the code. Maybe spacetime isn't smooth. Maybe it's pixelated at the smallest scale. Maybe physical constants have limits, like rounding errors. Some say to look at high-energy cosmic rays. For anomalies, critics say this isn't science, it's a philosophical puzzle, it's unfalsifiable. Even if we found a pixel, how would we know? It might just be a property of our universe. The real one, the argument exposes something deeper. It challenges the idea of a base reality. If we're in a sim, the laws of physics aren't fundamental. They're just the local rules, the code. Our search for a theory of everything might just be reverse engineering someone else's software. That leads to questions. If we're simulated, do our choices matter? Is consciousness just an algorithm? The paradox doesn't give answers. It holds up a mirror to science itself. Science probes an objective reality. But what if that reality is contingent? Just a layer in a stack of simulations, It makes you think. The nature of reality might be the ultimate question. One our tools may never solve. We're left wondering, is every discovery an insight into the cosmos, or just a clue about the cage? Empty space isn't empty. It's a sea of potential. Quantum field theory says the vacuum is a bubbling foam, virtual particles flickering in and out of existence. They borrow energy, exist for a moment, and vanish. That zero-point energy should fill every cubic centimeter of the cosmos with a colossal energy density. And when physicists do the calculation, they get a number. A prediction for the strength of this vacuum energy. Then they look at the sky. They measure the actual energy driving the accelerated expansion of the universe, what we call dark energy, the cosmological constant. The two numbers should be the same, but they aren't. They're catastrophically different. The theoretical prediction is 10 to the power of 120 times larger than what we observe. That's a 1 with 120 zeros. It's the single worst prediction in the history of science. Imagine calculating the force of a dripping faucet and getting an answer that predicts a planet-shattering tsunami. The mismatch is that insane. This is the vacuum catastrophe. If the vacuum energy were anywhere near the calculated value, the repulsive force would have been so immense the universe would have blown itself apart in a fraction of a second after the Big Bang. No stars, no planets, no us. The fact that we exist means something is canceling out almost all of that titanic energy. But what? The leading candidate is a perfect, delicate cancellation. Maybe for every type of particle, there's a supersymmetric partner. A shadow particle. The positive energy from ordinary matter and the negative energy from these shadow particles could balance, leaving a net energy near zero. But we've looked. The Large Hadron Collider has found no evidence for these superpartners at the energies we can probe. So the cancellation, if it exists, remains hidden. Or maybe our understanding of gravity is wrong on the largest scales. Maybe Einstein's cosmological constant isn't a property of empty space, but a symptom of gravity behaving differently across cosmic distances. Some modified gravity theories try to explain dark energy this way, doing away with the vacuum energy problem entirely, but they have their own challenges. The vacuum catastrophe is a screaming alarm. It tells us that quantum field theory and general relativity, when put together, produce a result that's not just slightly off, but unimaginably, uselessly wrong. There's a piece missing. A principle so profound it makes 99.999%. With 129s of the universe's latent energy simply disappear. What unknown law of physics performs this miraculous cancellation? Or are we, in our arrogance, measuring the shadow of a mechanism we cannot yet comprehend? The silence of empty space holds the loudest contradiction in all of modern physics. An astronaut is floating in space, it's cold, then they fire the rockets. They accelerate, and according to quantum field theory, something happens that shouldn't be possible. The astronaut starts to feel warm. A kind of thermal radiation appears around them, warming the ship. But another astronaut, just drifting nearby at constant speed, sees none of that. No heat, no particles, just empty space. For one, it's a sauna. For the other, it's absolute zero. That's the Unruh Effect, a prediction by William Unruh. It shows temperature isn't absolute, it's relative to your motion. Acceleration can create particles from nothing. Or from what we call empty space, these seething quantum fields. Put a sensitive detector on that accelerating ship, a kind of thermometer, and it gets jostled by the quantum activity in a specific way. It interprets that jostling as particles, as real, warm radiation. This isn't just math. It's tied to Hawking radiation. Stephen Hawking showed the intense gravity at the edge of a black hole, pulling on spacetime, has a similar effect to acceleration. The Unruh effect uses the equivalence principle, Einstein's idea that acceleration feels exactly like gravity. So accelerating through space is like standing in a gravitational field. If acceleration can pull particles from the vacuum, so can gravity. That's the seed of Hawking's prediction. A black hole's gravity can tease apart a virtual particle pair, making one real. The Unruh Effect is a simpler version of that. It tells us particles aren't fundamental building blocks in the way we thought. They're excitations, ripples in fields. And whether you see a ripple or just calm water depends on how you're moving. Are you floating with the current or racing across it? This shatters the idea of an absolute vacuum. What you call empty is full of potential reality, waiting for the right observer to bring it into being. It raises a question: is there any objective stuff out there, or is the universe's particle content just a matter of perspective? The warmth felt by an accelerating astronaut is as real to them as the sun on your skin. But it's a reality created by their journey. This paradox shows a flaw in our desire for a single, true description of the world. It suggests that at the quantum level, the universe isn't a stage with set pieces. It's a relationship, a dialogue between the observer and the field. And the script changes depending on how you choose to move through it. Someone gives a playwright a manuscript. It's leather-bound. Inside are 37 plays, 154 sonnets. He copies them out, word for word, and then he publishes them as his own work. Centuries later, a time traveler finds a copy of these works. They go back in time, and they give the manuscript to the young William Shakespeare. So who wrote Hamlet? The masterpiece, the information, it has no original author. It was never created. It just exists in this perfect loop. That's the Bootstrap Paradox. It's a trap for causality itself. The Grandfather Paradox is different. That's about physical events, changing something that could erase your own existence. The Bootstrap Paradox is about information or an object, with no discernible point of origin. The thing just pulls itself into reality. There's no first cause. The term comes from that phrase, pulling yourself up by your own bootstraps. An impossible feat. Here, information does exactly that. It is its own cause. And its own effect. In a universe with closed time-like curves where time can loop back on itself, this isn't just a story, it's a physical possibility. The equations of general relativity allow it. A book could be caught in such a loop. A blueprint, a symphony, even a person, in theory, they would have no true beginning. The film Predestination explores this. A character who is their own parent, their own child, their own recruiter. A closed circle of identity with no starting point. Interstellar touches on it too. The coordinates for the NASA facility are whispered across time by the very mission they made possible. The information creates itself. This presents a profound problem. Our whole understanding of history, of creation, of artistry, it relies on a linear chain. Cause and effect. A composer is inspired, writes a score. That's the cause. The symphony is performed, that's the effect. But in a bootstrap, the score exists because the performance exists. And the performance exists because the score exists. Which came first? The answer is neither. The loop is all there is. This challenges deterministic models of the universe. If everything is predetermined, could all of history be one giant, complex bootstrap? Could the laws of physics themselves be bootstrapped, with no initial creator? Just a self-consistent set of rules that mandate their own existence. It forces a question. Is the concept of an original creator for anything, from a play to the cosmos, is it a necessary idea? Or just a comforting story we tell because we experience time in a straight line? Can something truly come from nothing, if that nothing includes the twisted geometry of time itself? The Bootstrap Paradox doesn't threaten logical consistency, not like the Grandfather Paradox might. The timeline remains perfectly consistent, but it leaves a haunting emptiness where a source should be. It exposes something. Our deep-seated need for a first cause, an uncaused cause, that might be a flaw in our thinking. Not a feature of the universe. What if creation is not an event but a shape? The warmth from acceleration feels real, but it depends on a journey. That dependence on perspective. It echoes something deeper. About time itself, we all feel that flow, past to future. We remember yesterday, we can only guess at tomorrow. You can scramble an egg in an instant. But no amount of waiting will see it reassemble. That seems like the most fundamental rule, the arrow of time. But then you look at the fundamental laws. Newton, Einstein, quantum mechanics, they're almost perfectly time-symmetric. The equations work just as well if time runs backward. A film of two planets orbiting, it looks perfectly natural played in reverse. So why does our world have such a powerful, one-way direction? That's the Low-Entropy paradox, named for the physicist who challenged Ludwig Boltzmann with it. If every microscopic collision is reversible, how does irreversible behavior emerge for anything larger than an atom? Boltzmann's answer was statistical. It changed everything. He didn't look at individual particles, he looked at crowds. Think of a brand new deck of cards, perfectly ordered by suit and rank. That's a state of very low entropy, a measure of disorder. Shuffle it once, the order is gone. Shuffle it 1,000 times, the deck becomes a random mess. A state of high entropy. The crucial point is this: there's only one way for the deck to be perfectly ordered. Ace through king of hearts, then diamonds, and so on. But there are an astronomical number of ways for it to be in a messy, disordered state. Probability dictates that if you randomly arrange the deck, you are almost certain to get a high entropy mess. The universe works the same way. Particles move from ordered, low probability arrangements to disordered, high probability ones. That increase in disorder is the increase in entropy. And it defines the thermodynamic arrow of time. Scrambling an egg mixes the yolk and white into a more probable, disordered state. Seeing it unmix would be like seeing a shuffled deck spontaneously return to perfect order. Not impossible, but so staggeringly unlikely that you could wait longer than the age of the universe and never see it happen. But this leads to a question. If the increase of entropy points the arrow, what pointed the arrow in the first place? Why was the early universe in such an incredibly ordered, low-entropy state? The smooth, hot soup of the Big Bang was far more ordered than any of the complex structures that came later. Stars, galaxies, living things. That initial condition is the ultimate wound-up spring. Everything since has been the universe unwinding, exploring every possible disordered state as it expands and cools. Our entire experience, cause and effect, memory, aging, may be a consequence of our cosmos starting in this special, low-entropy configuration. We are not just moving through time, we are moving away from that singular moment of order. Some physicists, like Sean Carroll, suggest that if the universe is eternal or part of a multiverse, our Big Bang might have been a rare fluctuation. From a higher entropy equilibrium, a temporary bubble of order in an otherwise chaotic eternity. In that vast picture, the arrow of time might even reverse in other regions. With creatures they're remembering what we call the future. This idea ties back to Boltzmann brains, those freak fluctuations that seem more probable than our long, coherent history. The Low-Entropy paradox exposes the flaw. In thinking the fundamental laws alone can explain the flow of time. The laws provide the rules of the game, but the direction comes from the initial setup of the board. It forces cosmology to answer a question once reserved for philosophy. Why does time have a direction at all? The answer may not be in the equations of motion, but in the forgotten boundary of our cosmic dawn. The statistics of crowds, they only go so far. A single particle can trap logic in a maze. Lucian Hardy, a physicist, he designed a thought experiment. A kind of quantum maze. It leads to a conclusion that seems to break reason. It asks if a particle and its antiparticle can meet, and yet not destroy each other. An event that both happens and does not happen. That's Hardy's paradox. It pushes quantum weirdness past strangeness into something logically impossible. To see it, picture a simple maze for light. An interferometer. It splits a single photon, sends it down two paths at once. The paths are like the two arms of a letter L. They meet again later at a crossroads. There, the photon's two possible selves can interfere. If the paths are set just right, the photon's wave like nature means it always emerges from one exit, never from the other. It's a predictable dance of probability. Now make it a duel. Send in not one photon but two, a particle and its antiparticle. For this, an electron and a positron each gets its own interferometer. Their paths are set to cross at one precise point in the middle. If they ever meet at that crossing, they annihilate. A flash of light. Total destruction. The experiment is tuned so that if annihilation were possible, it would stop the particles from reaching certain final detectors. This is where the paradox is born. Through post-selection of data, looking only at the rare cases where both particles are detected at specific, non-annihilation exits, the math tells a contradictory story. To get that result, logic forces three inferences. First, the electron must have taken one particular path. Second, the positron must have taken its own particular path. And third, crucially, those two paths are the ones that cross. They are the very paths that lead to certain annihilation. Yet, because we detected both particles at the end, they clearly did not annihilate. So we're forced into a box. The setup and the final result imply the particles must have been on the collision courses, but the fact we detected them means they could not have been. It's a logical contradiction. An event that, according to the inferred history, should have happened, demonstrably did not. This cuts to the heart of what we mean by reality. It tests a concept called counterfactual definiteness, the idea that we can meaningfully talk about what would have happened in a scenario that didn't occur. In our everyday world, this is sensible. If you didn't take the bus this morning, we can still discuss the route the bus would have taken. In Hardy's experiment, that kind of reasoning leads directly to nonsense. Different interpretations of quantum mechanics scramble to resolve it. The many worlds theory has a ready answer. In some branches of the multiverse, the particles did annihilate. We, in this branch, simply happen to be in one of the rare, non-annihilating histories that still produced a detection. The contradiction is an illusion from our single-branch perspective. The pilot wave theory offers another escape. It says particles have definite trajectories guided by a wave. It suggests the particles never actually took the conflicting paths. Their guiding waves interacted in a way to steer them clear, while still making it look like they should have collided. But both solutions come at a cost. Many worlds asks us to accept an infinity of unseen universes. Pilot wave requires a hidden, non-local mechanism guiding every particle. Hardy's paradox exposes a deep flaw in our intuition. We want to tell a story about what the particles did when we weren't looking. We want to assign them a definite history, a trajectory. This experiment screams that such a story might be forever out of reach. The particles are not little marbles with secret paths. They are possibilities that resist being pinned down, even in retrospect. Does this mean reality is logically inconsistent at its core? Or does it mean our classical logic, built from a world of definite objects, is simply the wrong tool for the quantum realm? The paradox doesn't just make reality strange. It suggests the very framework we use to reason about cause and effect may crumble when applied to the isolated heart of a single quantum event. There's this ancient Greek hero, Achilles. He's fast, and he's challenged to a race against a tortoise, a slow-moving tortoise. Zeno of Elea presents this puzzle. He gives the tortoise a head start. For Achilles to catch it, he has to first reach the point where the tortoise began. But by the time he gets there, the tortoise has moved forward a little. So Achilles has to reach that new point. And again, the tortoise has crept ahead. This process repeats, endlessly. Achilles has to complete an infinite number of these smaller journeys before he can catch up. Zeno argues that completing an infinite number of tasks is impossible. So motion itself is impossible. The swiftest runner can never overtake the slowest. This is the dichotomy paradox. It cuts to the core of space-time infinity. It suggests the smooth, continuous motion we experience is an illusion, a profound illusion. For over 2 millennia, this paradox haunted philosophy. It challenged the idea of a continuum, the notion that any distance or duration can be divided infinitely. If space is infinitely divisible, Then between any 2 points lies an endless series of halfway marks. How could we ever traverse that? The resolution came from mathematics. In the 17th century, Newton and Leibniz developed calculus. They introduced the concept of a limit. They showed an infinite series of ever smaller quantities can sum to a finite total. Think of walking toward a wall. You cover half the remaining distance with each step. First 1/2, then 1/4, then 1/8. The distances are 1/2, plus 1/4, plus 1/8, plus 1/16. This series goes on forever, yet its sum is not infinite. It converges to 1. You reach the wall. The infinite subdivisions of space are matched by infinite subdivisions of time, and they shrink together. The time it takes to cover each halved distance also halves. So the infinite number of tasks takes a finite amount of time. Calculus provided the tool to describe motion through a continuum. It showed infinity, when handled correctly, is not a barrier but a description. But did it solve the paradox or just sidestep it? The mathematical answer is clear. Yet our intuition still stumbles. This is where modern physics enters. Quantum mechanics, theories of quantum gravity, suggest space and time might not be a smooth continuum at all. They might be pixelated, discrete. There might be a smallest possible unit of distance, the Planck length, and a smallest unit of time, the Planck time. If this is true, then Zeno was asking the wrong question. Space cannot be divided infinitely. There is a final, indivisible step. Achilles would not face an infinite regress of halfway points, but a finite number of tiny quantum jumps. Imagine a video game. The motion on screen looks fluid, but it's composed of a rapid sequence of still frames. At 60 frames per second, your brain blends them into continuous motion. The universe might operate on a frame rate so fast, Planck time is about 10 to the negative 43 seconds, that the illusion of continuity is perfect. So is motion an illusion, in a sense, yes, but not in the way Zeno thought. The illusion is not that motion doesn't happen, but that it is smooth. Our experience is a macroscopic average of countless microscopic, discrete events. Zeno's paradox exposes a flaw in how we conceptualize reality. It reveals the tension between our lived experience of a flowing, continuous world and the granular descriptions from our best mathematics and physics. Do we live in a continuum or a vast, cosmic digital display? The answer still eludes us, a puzzle from 2,500 years ago, still probing the fabric of space-time. The heart of a black hole is a final place. It's where the map of reality tears. In Einstein's general relativity, matter collapses under its own gravity. It gets crushed to a point of zero volume, infinite density. That's the singularity. The curvature of spacetime becomes infinite there. The equations we use for the cosmos, they just give nonsense answers. Space and time, they're the stage for everything. They stop having meaning. They aren't just warped, they're destroyed. The singularity is a mathematical scream. It means our physical laws have broken down completely. Roger Penrose worked with Stephen Hawking on this. He proved it wasn't just a quirk of perfect symmetry. His singularity theorems showed something. Under very general conditions, once an event horizon forms, a singularity is inevitable. It's a fundamental prediction, not an artifact, and it represents the ultimate failure of predictability in physics. At the singularity, you can't use the present state to calculate the future or reconstruct the past. The chain of cause and effect is severed. Anything that falls in has its history erased, not just from the outside universe. From the deterministic fabric of reality itself. To get the paradox, think of a navigator's chart. You sail toward a coordinate. The map shows the coastline, the depths, everything. But as you reach a specific point, the parchment rips, the ink bleeds, the lines dissolve. You can't say what lies beyond that tier, or even if beyond or location apply there. The singularity is that tier in space-time. Our theory of gravity gives us a magnificent map of the cosmos, but it tells us the map becomes unusable at the very center of its most fascinating feature. This flaw is so profound that physicists proposed a kind of cosmic safety rule. The cosmic censorship hypothesis, also from Penrose, it suggests nature abhors a naked singularity. It conjectures that every singularity is always hidden behind an event horizon, a point of no return that shields the universe from its lawless chaos. If a singularity were exposed, its unpredictable influence could leak out, making physics impossible anywhere. The hypothesis is unproven, but it underscores the desperation. We have to hope the universe protects us from the logical consequences of our own theories. What really lies at the center? The quest to answer that drives the search for a theory of quantum gravity. General relativity is a theory of the very large, planets and galaxies. Quantum mechanics rules the very small, atoms and particles. The singularity is where the very large meets the very small, where gravity becomes so strong it operates at quantum scales. Our two great theories are utterly incompatible here. String theory, loop quantum gravity. Other approaches their attempts to weave them into a single fabric that doesn't tear. They suggest the singularity might be replaced by a fuzzy quantum gravitational core, a Planck star or a bounce, where matter reaches a maximum density and rebounds. But we have no experimental data, no observations from beyond the horizon to guide us. The black hole singularity is the most glaring flaw in modern science. It's a monument to our ignorance, sitting at the center of our most successful theory of gravity. Its existence is a direct challenge. It asks whether our search for a single, elegant set of laws for the universe is a fool's errand, or if we're on the cusp of a revelation that will redefine existence itself. When our equations point to infinity, are they showing us a door, or just the limit of our own understanding? Watching water won't make it boil faster, but in quantum physics, watching something can stop it from happening. That's the quantum Zeno effect, named for an old paradox about an arrow that's motionless at every instant. In the quantum world, this isn't just a logic puzzle. It's something you can measure. If you have an unstable quantum system, a particle about to decay, an atom ready to flip its state, and you observe it over and over very quickly, you can freeze it. The constant measurements reset its evolution clock. It's like asking a coin mid-flip, "Are you heads yet?" And the asking forces it back to tails again and again. This comes from wave function collapse. When you're not looking, a quantum system evolves smoothly. Probabilities shift like a wave spreading, but a measurement is a violent interruption. It forces the system to pick a definite state. All those possibilities collapse into one reality. Right after that collapse, the system starts evolving again from that new point. If you measure it again before it has time to change, you'll likely find it in that same state. Do that fast enough, and the system never gets a chance to evolve. It's trapped, and this has been shown in labs, with trapped ions with atoms. Scientists use precise laser pulses to measure an atom's energy state repeatedly. Fire those pulses fast enough, and you can stop the atom from transitioning to a different energy level. They've frozen a quantum jump in place just by watching. There's a nuance here between strong measurements and weak ones. A strong measurement is the classic kind. It fully collapses the wave function. A weak measurement is gentler. It takes just a tiny bit of information with minimal disturbance. The quantum Zeno effect usually relies on strong, frequent measurements, but even weak measurements, if done continuously, can slow a system's evolution. That's sometimes called the watched pot effect. This has practical implications for quantum computing. A quantum computer uses fragile qubits, which exist in superpositions. Their biggest enemy is decoherence, where they interact with the environment and lose their quantum state, collapsing into ordinary bits. The quantum Zeno effect could be a defense. By monitoring the qubits strategically, gently, you might suppress the errors that cause decoherence. Watching could protect the quantum information. Here, observation isn't a problem, it becomes a tool. Take a radioactive atom with a half-life of 1 minute. Left alone, there's a 50% chance it decays in that minute. But if you set up a detector to check every second, have you decayed yet? The math of the quantum Zeno effect suggests you could prolong its life. The constant resetting of its quantum clock keeps it undecayed longer than nature intended when no one's looking. That forces a question back. Does consciousness play an active role in shaping reality? The Copenhagen interpretation always hinted that measurement creates reality. The quantum Zeno effect shows measurement doesn't just create it. It can sustain it or prevent it. The observer isn't a passive witness reading a dial anymore. They become an active participant, a gatekeeper whose attention determines what's allowed to happen. This paradox shows a flaw in any model of physics that treats consciousness as a side effect. It suggests that at the most fundamental level, the universe isn't a clockwork mechanism ticking on, indifferent to us. It's a responsive, participatory phenomenon, where the act of looking is woven into the fabric of what is. Galaxies aren't behaving the way they should. Take a spiral galaxy like our own Milky Way. Stars out on its edges are orbiting the center at tremendous speeds. Newton's laws say the only thing holding them in is the gravitational pull from all the visible matter. The stars, the gas, the dust we can see. But when you do the math, there's a mismatch. The outer stars are moving way too fast. There just isn't enough visible mass in the galaxy to create the gravity needed to keep them from flying off. The galaxy should be tearing itself apart. But it spins stable. That's the core of the dark matter paradox, a flaw in our cosmic accounting that's lasted for decades. The astronomer Vera Rubin gave the most compelling evidence in the 1970s. She measured the rotation speeds of stars in distant galaxies. The data was clear. Instead of the predicted drop in speed as you move out from the center, the rotation curves stayed flat. Stars far out were orbiting just as fast as stars near in. That could only mean one thing: there was far more mass in the galaxy than we could see. Mass that wasn't glowing in any light. It was dark. This invisible mass had to be in a vast, diffuse halo enveloping the whole galaxy, providing the extra gravitational glue. So the immediate solution was to propose a new form of matter: dark matter. It doesn't emit, absorb, or reflect light. It interacts with ordinary matter only through gravity. We can't see it, but we can see what it does. Its gravitational influence is everywhere. We see it bending light from distant galaxies' gravitational lensing, creating arcs and rings of distorted starlight. We see its imprint in the temperature patterns of the cosmic microwave background, the afterglow of the Big Bang. These observations suggest dark matter isn't just a galactic fix. It makes up about 85% of all the matter in the universe. The stuff of stars, planets, us, everything we know, is just a cosmic afterthought. For decades, the hunt has been on to find the particle. Candidates are out there, weakly interacting massive particles, WIMP actions, sterile neutrinos. Experiments deep underground in mines beneath mountains search for the faintest tremor of a dark matter particle bumping into an atom. Particle colliders, like the Large Hadron Collider, try to create them in collisions. So far, the detectors are silent. We've mapped dark matter's shadow through its gravity, but we've never touched its substance. This silence has led some physicists to a radical alternative. What if the problem isn't missing matter? What if it's a flawed law? A theory called modified Newtonian dynamics suggests that on the scale of galaxies, gravity behaves differently than Newton or Einstein predicted. It proposes a subtle tweak to the equations, a new constant. Apply Mond formula to galaxy rotation, and the flat curves emerge naturally without any invisible matter. For individual galaxies, Mond works remarkably well. It's an elegant solution that does away with the need for a mysterious particle. But elegance hits a wall with the broader cosmos. Mond struggles to explain the bullet cluster, two colliding galaxies. Observations show the visible matter, the hot gas, was slowed by the collision and sits in the middle. But the mass, mapped by gravitational lensing, has sailed right through and lies on either side. That's exactly what you'd expect if the mass were made of dark matter particles that barely interact. It's very hard for a modified gravity theory to explain how gravity can be strongest where there's no visible matter at all. Endman has a difficult time accounting for the precise patterns in the cosmic microwave background without adding extra components that look suspiciously like dark matter. Think of a wobbly chair. You sit down and it teeters. One approach is to assume there's an invisible leg, a support you can't see, holding it up just enough. That's the dark matter approach, inventing a new component. The other approach is to question the laws of structural engineering. Maybe, at this specific scale and weight, wood and metal behave in a way our textbooks never described. That's the MIND approach, changing the fundamental rule. Both are admissions of ignorance, so where does that leave us, with a paradox at the heart of physics? Is the universe mostly made of something we cannot see or interact with, revealing a flaw in the standard model of particle physics? Or is our grasp of gravity, a force we thought we understood from apples to black holes, somehow incomplete on the vast scales of galaxies? This isn't a minor puzzle. It's a fundamental gap in our inventory of reality. The answer won't just fill in a blank in a textbook. It will redefine what we think the cosmos is built from and force us to rewrite either the story of matter or the story of force itself. John Archibald Wheeler had this question. It feels like it bends time backward. He imagined a single photon moving through an interferometer. That's a maze of mirrors and beam splitters. The photon can take two paths. If you leave the final piece in place, a second beam splitter, the two possible paths overlap, they interfere. The photon acts like a wave. It shows it went both ways at once. But if you remove that final beam splitter, you can check which physical path it actually took. Then it acts like a particle. A single bullet down one corridor. The staggering part is the timing. You can decide whether to insert or remove that final beam splitter after the photon has already entered the maze. After it's already made its journey in classical terms, yet the result you get, wave or particle, seems to be determined by your choice, a choice made in its future. It's as if the photon's past is waiting, undefined, until you decide how to look at it. Wheeler called this the delayed choice experiment. He said we live in a participatory universe. The idea isn't that we create reality from nothing. It's that the universe only becomes definite through acts of observation, even observations that come late. This isn't just a thought experiment anymore. Quantum optics labs have done it, with photons traveling over vast distances. In one version, light from a distant quasar travels for billions of years. Then it's subjected to a delayed choice measurement here on Earth. The implications are profound. They challenge the very existence of a definite past. In a block universe where past, present, and future all exist timelessly, there's no paradox. The entire experiment is fixed. The photon's emission, its journey, your late choice, they're all parts of a single, static, four-dimensional block. Your feeling of making a free choice is an illusion. The outcome was always written. But if we reject that deterministic picture, we're left with a dizzying possibility. Retro-Causality, the idea that a measurement now can ripple backward in time, to influence what happened then. It suggests the present isn't just a product of the past. It is a co-author of it. Think of a detective investigating a crime from last night. She has two suspects. She can choose today to look at one specific piece of evidence. If she examines the security camera footage, she defines the crime as a solo act, one suspect caught on tape. If she instead chooses to analyze the complex financial records, she defines the crime as part of a deep conspiracy between the two. Her choice of investigation today after the event determines the nature of the crime that was committed. Not the fact that it happened, but its character. Its story. Was it a simple burglary or an elaborate fraud? In Wheeler's experiment, the delayed choice doesn't change the fact that a photon went through the apparatus. It changes whether its journey was a wave-like conspiracy of possibilities or a particle-like solo act. So what does this say about history, about our own past? Does the moon exist when no one is looking? The delayed choice experiment pushes that question further. Did events have definite properties before we looked back at them? Or is history a kind of quantum manuscript, its ink still wet, waiting for our present attention to give it a final, readable form? This paradox exposes a flaw in our storytelling. We are wired for linear narratives, cause then effect, past then present, but at the quantum bedrock, that sequence may be a comforting fiction. The universe may not keep a single objective ledger of what happened. It may keep a ledger of possibilities, and only settle the accounts when a question is asked. The present isn't just reading the book of the past, it might be holding the pen. The cosmic microwave background is a picture of the universe when it was very young, and its temperature is almost the same everywhere you look. But that sameness is a problem. Because the universe is so big, the farthest points we can see in opposite directions are over 90 billion light-years apart. Light has only had 13.8 billion years to travel. So those two regions have never been in contact. They've never exchanged heat. They're causally disconnected, and yet they're the same temperature. They're in perfect thermal equilibrium. That's the horizon problem, and it means the standard Big Bang model is incomplete. It can't explain this smoothness without assuming very special starting conditions. In the late 70s, Alan Guth saw this flaw. He proposed a fix, a single idea, cosmic inflation. He said that in the first tiny fraction of a second, the universe went through a period of exponential expansion. Faster than light. Not matter expanding into space, but space itself stretching. Imagine a tiny patch of the early cosmos, smaller than a particle, but perfectly smooth and uniform because it was so small every part was in contact. Then inflation happens. That tiny patch is stretched by an enormous factor, at least 10 to the 26. It becomes larger than our observable universe in less time than light crosses a proton. Think of a balloon with a single, uniform dot painted on it. Before you inflate it, the dot is tiny. Its smoothness is trivial. Now blow the balloon up to the size of the Earth. That single dot now stretches across the entire surface. Every point shares the same properties because they came from the same original dot. That's what inflation did. It took a microscopic region that had smoothed itself out and stretched it to cosmic size, creating the large-scale uniformity we see. The horizon problem vanishes because the whole sky was once a single neighborhood. Inflation made other predictions. It said the universe should be geometrically flat, and observations of the cosmic microwave background have confirmed that. It also predicted the specific pattern of tiny temperature fluctuations in that radiation. The seeds for galaxies. Satellite missions have mapped these fluctuations, and they match inflationary theory with precision. But this success has a cost. Was inflation an elegant solution or just a fix? Does it expose a flaw in the Big Bang's starting point? The theory requires a new field, the inflatoned field, that drove the expansion and then decayed away. We haven't observed this field. We infer it because without it, our model can't explain its most basic feature. It's a paradox that forced physicists to invent a new chapter of cosmic history. A chapter we're still learning to read. The horizon problem reveals a hidden dependency. Our story of the Big Bang relies on a prologue of unimaginable violence. A prologue we can only reconstruct from echoes. It asks whether we've uncovered a deep truth about creation, or just crafted a beautiful story to cover the gaps in our knowledge. The smooth sky above us, a testament to the universe's ingenious simplicity, or to our own desire to make it make sense. These 20 paradoxes aren't just random quirks. They're symptoms, a kind of fever in the body of science, and they point to something deeper, an illness in our understanding. Each one, from the twin paradox to the delayed choice, it feels like its own puzzle. But if you step back, you see they cluster around the same fault lines, the same cracks in the foundation. In modern physics, they're the places where our two greatest theories, quantum mechanics and general relativity, they just refuse to speak to each other. They're the moments where our intuition about time, about causality, about reality itself, it just shatters against the evidence. These aren't separate problems. They're different expressions of the same fundamental incompatibilities. Think of modern science as a ship, a magnificent ship. For decades, even centuries, it sailed smoothly across a sea of discovery, mapping the cosmos with beautiful equations, but now it keeps hitting icebergs. Each paradox is an impact, and each iceberg looks different above the water. But below the surface, they share the same structure. A massive, hidden structure. That structure is our incomplete knowledge. The twin paradox, the grandfather paradox, those are icebergs of time. The measurement problem, Hardy's paradox, those are icebergs of quantum reality. The vacuum catastrophe, the dark matter paradox, those are icebergs of cosmology. Each collision is a warning that something vast and unseen lies beneath our voyage. The philosopher Thomas Kuhn called these anomalies. In his view, science doesn't progress in a straight line. It operates inside a paradigm, a set of accepted theories, methods, assumptions. For a long time, the paradigm works. It solves puzzles, but eventually, anomalies accumulate. Facts the paradigm can't explain, not without becoming hopelessly complex. Patched together, these paradoxes are our anomalies. They're the experimental results, the logical results, that our current paradigm strains to contain. A paradigm built on separate pillars. Quantum theory, Einstein's gravity. Kuhn argued that when enough anomalies gather, they trigger a crisis, and from that crisis, a scientific revolution is born. A new paradigm emerges, one that can explain the old data and resolve the anomalies. The shift from Newton to Einstein was one such revolution. Are we living through another? Look at the groupings, the paradoxes of time, from the twins to the arrow of time to the bootstrap. They all challenge our linear, common-sense view. They suggest time might be emergent, a side effect of entropy, or even an illusion from our limited perspective. The quantum reality paradoxes, Schrödinger's cat, the EPR paradox, the quantum Zeno effect. They all revolve around observation. They ask if reality exists independently of being measured, and whether consciousness plays a role in its formation. The cosmological paradoxes, Fermi, Olbers, the vacuum energy, they ask the biggest questions. They probe the initial conditions of the universe, the nature of empty space, our place in a possibly silent cosmos. Each cluster points to a core question, a question our current science cannot fully answer. So the ultimate question these paradoxes force on us, it's not about any single mystery. It's about the future of knowledge itself. Are these 20 contradictions just puzzles, to be solved within the current framework with a little more cleverness? Or are they the glaring, persistent flaws, the ones that signal the end of an era? Are we standing on the precipice of a paradigm shift, one as profound as Copernicus or Newton or Einstein? The pattern in the paradoxes suggests the latter. They're not scattered holes in a solid wall. They're the cracks showing the wall was built on unsettled ground. The next revolution won't just fill a gap. It will demand we rebuild our conception of reality from its very foundations, offering a new story where the cat is neither alive nor dead, where time has no arrow, where the vacuum hums with the secret of everything, not because the paradoxes are strange, but because our current vision of the cosmos is simply too small. These paradoxes aren't failures. They're our most valuable tools. Each contradiction, each logical knot, it's a clue. A flare sent up from the edge of what we know, lighting up exactly where our maps go blank. They don't show science is broken, they show it's working. This is how discovery happens, not by polishing something perfect, but by finding the cracks and asking what's underneath. The big themes come through now. The relativity of observation, how reality shifts with the viewer. The illusion of a single timeline replaced by this tapestry of possibilities. And then the incompleteness, this haunting sense that our best theories are like magnificent cathedrals, but unfinished. To embrace these mysteries is to fuel progress. It takes humility. The universe doesn't owe us explanations that feel intuitive. Richard Feynman said it. He said, "I think I can safely say that nobody understands quantum mechanics." He didn't mean we can't use the math or make predictions. He meant the true nature of that reality, what the equations describe. It escapes our classical grasp. That admission isn't surrender. It's an invitation to keep looking, to keep questioning, to never be satisfied with easy answers. So next time you look at the night sky, look with more than wonder. Look with a critical eye. See the darkness between the stars and remember Olbers' question. Watch a satellite glide by and think of the twin paradox, time stretching and compressing in orbit. Feel the ground under your feet and consider its mostly empty space, seething with quantum potential, held together by forces we're still struggling to name. Each paradox is a lens, a way to see the familiar world as the profound mystery it is. This journey through 20 ideas, it's just a beginning.